So hello everyone and welcome back to this DC to DC converter lecture series. So in the previous lecture, I had ended with this epic converter and I had taken a week's break because I had just finished my next Udemy course. So I needed to give my throat a bit of a break. So before I start off with the next one, I will give you as usual a brief background about the Udemy course. So this is the latest Udemy course which I just created, and that is Simulation of Magnetics for Power Electronics using Python. So in this course, I go through the entire theory of transformers, and I start off first with inductors. I go on to coupled inductors and then finally transformers, and eventually have one test case of flyback converter. So therefore, I am considering the case of a high frequency transformer in a power electronic circuit. And of course, besides this, I also have my usual course of simulating power electronic circuits using Python. And this is an entire course where I talk about everything, including the basics of installing the software, a little bit of basic theory of power electronics, and finally a case study of how to simulate a buck converter. And of course, there is the previous case, which is this one, that is basics of digital signal processing for power engineers. So this is more in case if you are interested something more on signal processing or control. And here I talk about how we can use Python to design filters, right? So these are the three courses which I have. And most importantly, this is the latest course, that is Simulation of Magnetics for Power Electronics using Python. I just released it just maybe a week back, right? 2 weeks back. So now that we're done with this basic theory, this is of course, as I said, if you are interested in video lectures, but you want something a little more comprehensive than just a YouTube video lecture series, you want an entire course. These are courses which I have on Udemy. The links for these courses are provided in the description of this video, right? So now to get back to the lecture. So now that we're done with the epic converter, the next converter that we're going to look at is the ZETA converter, right? And this again is probably the last DC to DC converter of the non-isolated series. After this, we'll start off with isolated converters. So to come to this, let me go over to my spreadsheet. And this is where we are, this is epic converter. Now, to understand how this ZETA converter works, we have to actually look at a few of them. So for example, let me go over. First, let me create a new folder. Let me call this ZETA converter. All right. So what I'm going to do is I'm going to go over to my spreadsheet, save this in the new folder which I've created, and this time I will call this the ZETA converter. And I'll just make sure that it's still a CSV file. And we have the new ZETA converter. So let me go over to this folder and I should have this. So as I said before, we have to convert it with several other. So I'm going to compare it with the Chook converter. And let me go open the Chook converter. This is the Chook converter. All right. Now, besides the Chook converter, we have also several other converters. But what is important about this SEPIC, the Chook and the ZETA converter is that they all use the decoupling capacitor C1, which is bang in the middle of the circuit, right? So let me go into the Chook converter and copy. Well, actually, let me copy this circuit completely. The reason why I want to do this is I want to compare how these circuits work. So I'm going to paste it here in the same file as the ZETA converter. All right. So let me just zoom out a little so that we can see it. And maybe just a little more. Okay, so this gives you at least an overview of how this looks like. Let me just delete one row so that I can get this in. Yeah, now at least I have both circuits. Now that we place these two converters one above the other, so the top one is the SEPIC and the bottom one is the Chook. So let us compare these two and try to figure out where the ZETA comes in. Now, in the case of a SEPIC, we already saw that when the switch is turned on, At least I would say that both the SEPIC and the CHOOK, they have the first stage common, right? Matter of fact, until the decoupling capacitor, they are common. It only changes afterwards, right? So when the switch is turned on, the voltage source charges the inductor through the switch. So the current flows in the clockwise direction. This is the same for both the SEPIC and the CHOOK, right? It's the same performance. So the current through the inductor rises, the inductor charges up. Now, what happens on the other side differs a bit. In the case of a SEPIC converter, the capacitor discharges through the switch and charges the inductor, right? So the current flows in the counterclockwise direction, and the current in the inductor flows upwards and it gets charged. The diode does not conduct, right? The diode does not conduct, so the output capacitor is disconnected from the rest of the circuit, right? In the case of a CHOOK converter, when the switch is turned on, the capacitor discharges through the switch and flows through the output capacitor, right? So therefore, the current direction is also the counterclockwise direction, but in this case, the current is flowing through the output capacitor. And since the current is flowing through the output capacitor in the upward direction, the polarity of the output is reverse. In the case of a SEPIC, the polarity of the output is the same as the polarity of the input. Now, when the current flows in the counterclockwise direction, again, the inductor L2, should just probably pull this a little, the inductor L2 charges up. So in both cases, when the switch is turned on, inductor L2 is charged, both the SEPIC and the CHOOK, right? Only difference is, in the case of a SEPIC, the capacitor is not connected to the rest of the circuit. In the case of a CHOOK, the capacitor is connected to the rest of the circuit, right? The capacitor, decoupling capacitor C1 is charging the output capacitor and the inductor L2. When the switch is turned off, let's compare these two. This SEPIC converter now has a forward path. So for example, the voltage source is now connected directly to the output through this forward path, through the decoupling capacitor and the diode. The diode conducts because the polarity of the diode is such that the cathode is towards the right. So the current flows in the right. So therefore, now the voltage source and the inductor are charging the output, this decoupling capacitor and the output capacitor. And at the same time, the inductor L2, which was charged in the previous cycle, right, now starts discharging through the output capacitor through this diode. So the output capacitor now gets energy from three sources: the input voltage, the inductor, and also this inductor. So both inductors and the input voltage source. In the case of a CHOOK converter, things are slightly different. When the switch is turned off, the voltage source now conducts through this diode, right? The diode in this case is such that the polarity is downwards, right? So therefore, this diode is going to bypass all the current that is flowing from the voltage source and the inductor. Because remember, current will always flow through the path of least resistance, and the diode provides this path of least resistance. So here in the case of a CHOOK converter, when the switch is turned off, the input voltage is not directly connected to the output voltage. The input voltage again flows, the current again flows through the diode, and it is the inductor L2 which is also freewheeling through the diode, right? And of course the capacitor also. The capacitor is being charged by the input voltage and the inductor through this diode. So this is how it works. Now, how is a ZETA converter any different? Let me change the first SEPIC converter to a ZETA converter, right? You could do either of them, but let's do that first. So in the case of a ZETA converter, the first stage is similar to a buck. So what that means is the switch is moved out and comes in the series path. So let me just delete a few of these. The inductor comes here. right? This is the inductor. The switch now comes in the series path. This is the change of a ZETA converter. So when the switch is now turned on, the voltage source will feed the inductor, but at the same time, it will also feed the rest of the circuit. Right? In the case of a SEPIC and a CHUK, when the switch is turned on, the input voltage is not connected to the rest of the circuit. In the case of a ZETA, the input voltage is now connected to the rest of the circuit as well, and it is also feeding the inductor. Right? The decoupling capacitor remains exactly where it is. The change comes again in this last branch. Here again, I will just cut this out and place it here. The inductor comes in the series path. And the diode comes in the parallel path. So this is a ZETA converter, the one above, right? Now, let's try to figure out what's going to happen. We already said when the switch is turned on, the voltage source charges the inductor in the clockwise direction, right? But at the same time, when the switch is turned on, this is really a parallel circuit. So there is nothing stopping the current from flowing in the forward direction as well. So therefore, the voltage source does connect to the rest of the circuit, which means it charges the capacitor C1 and also it charges the inductor L2 as well as the output capacitor. So therefore, the input voltage is feeding everything. It is charging the inductor, it's charging the capacitor, and charging the last inductor as well, and also the output capacitor. When the switch is turned off, now the input doesn't appear anywhere in the circuit, right? Now, it is the capacitor that matters. The capacitor will discharge through the inductor. So both the capacitor and the inductor will discharge, but here there's the interesting catch. The diode is now in such a polarity, it is reverse compared to the CHUK. In the case of a CHUK converter, the diode polarity was such that the cathode was downwards. In the case of a SEPIC, the ZETA, the diode is such that the polarity is upwards. So therefore, the capacitor the inductor and capacitor are now going to flow through this diode series, this series path, right? So therefore, now what happens? The inductor here, right? The inductor, which was carrying a current towards the right, will also freewheel through this diode, right? So therefore, the inductor is charging the output, is discharging, and therefore is sort of feeding its energy to the output capacitor and is freewheeling through the diode. So therefore, this is how a ZETA converter works, right? So again, maybe a little vague, but best we'll know when we simulate it, as always. So now that I've done with this, let me just zoom in a little. This is where we were, right? And this is pretty much the circuit. The rest of it is almost the same. Only you see we've just switched the position of some of the elements, right? The inductor, which was in the series path, is now in the parallel path. The switch was in the parallel path, is now in the series path. The decoupling capacitor stays exactly where it is. The diode has switched with the inductor, and the diode has reversed in polarity. The advantage of a ZETA converter with respect to a CHUK converter is the polarity of the output is still the same as the polarity of the input. The output voltage has not reversed, right? So therefore, you can ground one terminal completely. It is possible, right? Now, I've been talking for a while, so let me go over to my web browser and create this new simulation. So I'll just call it ZETA converter. And as before, I'll leave the time duration as 1 second. I will leave the integration time step also as 1 microsecond. I will decrease the time step of data storage to be the same as the integration time step. Now coming to the directory, all I have to do is come over here, go to my newly created directory. This is the ZETA converter. Go to properties. Copy it, go back to my web browser and paste it, right? And the simulation parameters have been saved, which means it has been successfully taken. So now I can come and just add this ZETA converter. So I'll just go to my new folder, call it ZETA converter, save the file, and let's process the circuit schematic. And the circuit does not have any detectable errors. So we are good to go. So as before, I would suggest take some time and try to figure out with a pencil and paper how this would work. Now, details as always will come out when we simulate, and that's the purpose behind this entire video lecture series, to learn power electronics by simulation. So therefore, if things are a bit confusing right now, things should become a little clearer later. The idea is that I wanted to put together the SEPIC and the CHUK and talk about how these two can be merged to form a ZETA. Of course, there are several implications of the position of these elements and how that matters in the performance of the converter. And we'll talk about that very soon. But for now, I'm going to end this lecture as it's been pretty long already. If you have any doubts, please do post in the comments or message me on social media or send me an email, whichever is your preference. Or in the next lecture, which will be next week, I will continue this and we will start editing the circuit parameters and eventually we will simulate it. So thank you so much for watching and goodbye for now. See you next week.